In this video we're going to discuss proof by induction. So proof by induction is based on the principle of mathematical induction, which states that if P of n is a mathematical statement that's either true or false for every natural number n, and the following two conditions are true, if it's true that P of 1 is true, and whenever P of n naught is true, then P of n naught plus 1 is true, then the statement P of n is true for all natural numbers n. The principle of mathematical induction can be proved using the well-ordering principle over the natural numbers. In this video, we're going to discuss what a proof by induction looks like and give a couple of examples. A correct usage of the principle of mathematical induction, that is, a correct proof by induction, has the following form. A statement of the theorem to be proved, so some statement to the effect that for all natural numbers n, P of n. So that would be the statement that you want to prove. Two subproofs. A proof of P of 1, showing that the statement is true when n equals 1. That's known as the base case. And then the induction step, a proof that if P of n is true for some n equals n naught, then P of n is true for some n equals n naught plus 1. Okay? So if it's true for n naught, then it's true for n naught plus 1. And finally, a conclusion, a statement at the end of your proof, like therefore by the principle of mathematical induction, it's true that for all natural numbers n, P of n. Now, it's also helpful to begin your proof even before verifying P of 1 by saying something along the lines of proof by induction. It just lets the reader know what the method of proof is going to be and what structure to expect. A proof of the induction step is usually carried out in the most direct way. First, you assume P of n naught. So you assume what's called the inductive hypothesis. You assume the statement's true for n equals n naught. And then from that assumption, you derive P of n naught plus 1. You show that P of n naught plus 1 is true based on the assumption of P of n naught. So let's look at an example. Let's prove that for all natural numbers n, the sum of the first n natural numbers is equal to n times n plus 1 over 2. Proof by induction. Step 1, the base case. We want to show that for n equals 1, the sum of the first n natural numbers is equal to n times n plus 1 over 2. So let's assume n equals 1. Then the sum of the first n natural numbers, that's the sum of the first one natural number, which is just 1. So it's equal to 1. So let's look at n times n plus 1 over 2. If we plug in n equals 1 there, we'll get 1 times the quantity 1 plus 1 over 2, that turns out to be 1. So indeed, the statement is true for n equals 1. The sum of the first n natural numbers is equal to n times n plus 1 over 2 when n equals 1. So this completes the proof of the base case. Now let's go on to the induction step, step 2. Here we want to show if the statement is true for n naught, that is, if the sum of the first n naught many natural numbers is equal to n naught times n naught plus 1 over 2, then the statement is true for n naught plus 1. So then we want to show that if the statement is true for n equals n naught, then the sum of the first n naught plus 1 natural numbers is n naught plus 1 times its successor n naught plus 2 divided by 2. So to prove this, let's assume that the sum of the first n naught natural numbers is n naught times n naught plus 1 over 2. Let's consider the sum of the first n naught plus 1 natural numbers. We can look at the sum of the first n naught plus 1 natural numbers as the sum of the first n naught natural numbers plus n naught plus 1. So our earlier sum plus an extra term. Now we know that that smaller sum, the sum of the first n naught natural numbers, by our induction hypothesis, is n naught times n naught plus 1 over 2. Okay, so this next line here is true by the induction hypothesis. Now you can see we're trying to add n naught times n naught plus 1 over 2 to n naught plus 1. We can do that if we get a common denominator. So this is the same as n naught times n naught plus 1 over 2 plus 2 times n naught plus 1 over 2. Now you can see there's a factor of n naught plus 1 in the numerator of both fractions there, so we can factor that out, combine like terms, and this equals n naught plus 1 times n naught plus 2 over 2. So we've just shown that if the statement is true for n equals n naught, then the statement is true for n equals n naught plus 1, so that completes the proof of the induction step. So our conclusion is that the following: we've proved the proposition is true for n equals 1, and we've proved that if the proposition is true for n equals n naught, then it's true for n equals n naught plus 1. Therefore, by the principle of mathematical induction, we can conclude that for all natural numbers n, the sum of the first n natural numbers is n times n plus 1 over 2. Now, some statements are not true for all natural numbers, but are true for all natural numbers after a certain point. They're true for all natural numbers large enough. Induction does allow you to start at an arbitrary natural number, m, and then to prove that a statement is true for all natural numbers n greater than or equal to m. Here's a restated version of induction to cover such results. So let P of n be a mathematical statement that's either true or false for every natural number n. Let m be a natural number. If the following two statements hold, if P of m is true, and whenever P of n naught is true, then P of n naught plus 1 is true, then P of n is true for all natural numbers n greater than or equal to m. So you can see that this is the same as the original principle of mathematical induction. It's just that the base case is some natural number m, not necessarily 1. Then what we prove is that the statement is true for all natural numbers greater than or equal to that base case m. So proof using this version of induction will have the same structure. We'll just start at a different base case. Let's see an example. Let's prove that if n is a natural number and greater than or equal to 5, then 4 times n is less than 2 to the nth power. Proof by induction. Step 1 is the base case. We want to show that for n equals 5, the statement 4 times n is less than 2 to the n is true. Well, if n equals 5, then 4 times 5 is equal to 20, and 2 to the 5th is 32, so indeed it's true that 4 times n is less than 2 to the n. Now we go on to the induction step. We want to show that if 4 times n is less than 2 to the n when n equals n naught, then 4 times n is less than 2 to the n when n equals n naught plus 1. So let's assume that for n equals n naught, we have 4 times n is less than 2 to the n. That is, we're assuming that 4 times n naught is less than 2 to the n naught power. Now 4 is less than or equal to 4 times n naught, which by our assumption is less than 2 to the n naught. So 4 times a quantity n naught plus 1. Well, if we distribute the 4, that's 4 times n naught plus 4. We know by the induction hypothesis that 4 times n naught is less than or equal to 2 to the n naught. And by what we just said, we know that 4 is strictly less than 2 to the n naught. So 4n naught plus 4 is going to be less than 2n naught plus 2n naught. That's 2 times 2n naught, which is 2 to the n naught plus 1. Thus, 4 times the quantity n naught plus 1 is less than 2 to the n naught plus 1, if 4 times n naught is less than 2 to the n naught. Okay, so we've proved that the statement is true for n naught plus 1 if the statement is true for n naught. That's exactly what we had to do to prove the induction step. So we've proved the proposition is true for n equals 5, and we've proved that if the proposition is true for n equals n naught, then it's true for n equals n naught plus 1. Therefore, by the principle of mathematical induction, we can conclude that for all natural numbers n greater than or equal to 5, 4 times n is less than 2 to the nth power. So that concludes this video. Thanks for listening.